Hello, and welcome to Lesson 2 of the Generative AI course for venture capitalists. In this lesson, we will do a technical deep dive into a small portion of the systems used for deep generative AI. So it's important to note that generative AI is a type of machine learning that is usually focused on generating content, images, text, music, video, audio, code. It's a type of AI that's often used in these applications, natural language processing and so on. But the question is, how does it work? What are the pieces that go into creating a generative AI system? The first step that we need to understand is data. Specifically, we need to get a common vocabulary for talking about data. So in the general sense, it's information that is processed, analyzed by people or computers. Lots of examples here: numerics, text, images, videos, what have you. It can be used by people, computers, anyone, to answer questions, make predictions, and to support decision making. It's often collected and stored in databases as files on your machine. Some examples might include a Word document, a PDF, a JPEG, an entire movie, a row in a database describing a movie, how much money it made, the list of the actors who performed in the movie, the runtime, etc. So these are examples of individual instances of data. If you have maybe a folder with a bunch of Word documents or a folder with a bunch of PDFs, that is now a data set, a collection of data. It can be homogeneous, so all of them are text documents, all of them are Word documents. Or it can be heterogeneous, so you can have Word documents and images and videos all stored in the same database. One really important kind of data that gets talked about often is tabular data, often stored as an Excel document or a CSV. Another important word to know about when talking about generative AI and data is that of a distribution. So we see here a distribution of seed check size in millions of dollars by the Ultra VC investment firm. And so you can see this follows a somewhat normal distribution. Maybe the middle is around $6 or $7 million for seed check. This is interesting. So it tells us a few things. It tells us how the firm invests. They have quite large check sizes. That's in some instances, $11, $13 million for a seed round, quite a bit. They also have very small, very small check sizes, but most of the time they're somewhere in the middle. Now imagine you could synthesize this information into a generative AI. You could ask it to generate a seed check size. How much should you invest? Conditioned on maybe the VC firm doing the investing or information about the company. So an example of that might look like this. So we ask to do a seed check size. I'll move this over just a little bit more. And it says, tell me about the company. Okay. They synthesize audio of your loved ones who are far away, something like that. And then it says, all right, you should invest $4.5 million at an $11 million valuation. There is some logic going on behind the scenes here, potentially, or it could just be a black box. We really don't know. But that's an example of a generative AI system that uses data that you might be familiar with. So how does this work? Well, machine learning, specifically deep learning, plays a very central role in generative AI. In order to generate new content, a model must be trained on a large data set of examples. The training process measures the loss and optimizes the model to try and improve that loss so that your model can generate data at a higher quality. Every machine learning system has the same core building blocks, without fail, every single one. Model, performance criteria, a data set, and an optimization method. So the first thing you need is a model. People often name these GPT-3, StyleGAN, Stable Diffusion. These are all examples of models in some sense. You need a performance criteria. This is also called the loss function or the objective function, or in economics, sometimes it's called a cost function. This allows you to guide the model's generation based on their quality, with the hopes that quality improves over time. You also need a data set. These are usually, at least for today's models, internet scale. They are massive. They don't fit on a single computer or even a small collection of computers. You could take every laptop at your company and it probably would not fit combined all of the data used to train some of these models. This means millions or even billions of documents collected from a wide variety of sources. They can be unlabeled, or additionally you can pay people to generate or label the data for you if you can't find enough high quality sources. And then finally, you need a way to steer the model during training. This is called optimization. There are many flavors of optimization. There's lots of research. It's an active area of research. But at the core, they're usually using a technique called gradient descent. It's a fancy jargon term for showing the model the best way it can improve its generation on the next step. So you've shown it some data, you give it a score, and then the optimization criteria via gradient descent tells it how to improve on the next iteration. So let's walk through two examples. The first being a transformer. So the transformer was developed in 2017. The foundational paper was called Attention is All You Need. This was developed at Google, and it is the backbone for GPT-3, ChatGPT, Codex, Flan, Palm, Megatron, Bloom, and many, many other language models. It has something that's called an encoder or a decoder. Sometimes it has one or the other or both. These are a sequence of deep learning layers with attention and skip connection in between that form a significantly sized model. The objective of this model is quite simple. Predict the next word in a sentence. So if you feed it enough sentences, it will begin to learn English. It will learn concepts about the world. It will learn about translation. As an example, if you start training with the phrase, I went to the blank, and then you ask the model to complete the phrase, it might say moon or park or store. If it's doing a particularly poor job, it might say something like wallet or broccoli or something else improbable. You penalize it using this next word objective for improbable predictions, and then after billions or even trillions of examples in some case, it can get pretty good. It's somewhat fascinating, philosophically at least, that transformers that are extremely powerful models that power all of the translation services we use, a lot of the speech-to-text services that you use in your various assistants, they're all using next word prediction. It really is quite incredible how this simple system has given rise to lots of emerging. The data set could be a large set of documents. So for example, if you're training a code transformer, it's learning to predict the next piece of code that you would write. Get all of the code available to you on the internet, train it to predict the next word, and it gets really good at coding. Use all of the documents on the internet, all of the scientific papers on archive, or a proprietary data set. Maybe you have a set of legal documents that you care about. It is also trained with gradient descent, as many of these are. The next model is called a diffusion model. Calling it a single model is a little bit of a misnomer. It's actually multiple models. So you can have a UNet, a BAE, and a CLIP model all stitched together to form a single model, such as DALL-E or Stable Diffusion. The criteria here is actually slightly more complicated. The purpose of this model, at least in the image synthesis case, may be to match text descriptions to image output. They do so via a process called denoising. These are sometimes referred to as denoising diffusion models. But the criteria itself is to reverse a noising process. So you have an image and a description of that image. Let's say you have a dog, beautiful sweater. The text associated with this caption may be a dog, beautiful sweater in the park, etc. Take this known image and you add noise to it. So it eventually just looks like static on an old television. But because you were the one adding noise, you know exactly how much noise you added at each step, and so you can reverse that. In fact, you can train a model to reverse that in situations where you don't know how much noise was added. So at the end of the day, you can be given a text description of some image, and you can be given a blank image or a noisy image, and your model can diffuse the image until it resembles the text description. This is the technology that powers Stable Diffusion and DALL-E. They became viable in a paper called Diffusion Models Beat GANs on Image Synthesis that came out recently, and have since taken the world by storm. They are slightly newer than transformers and powerful. They're also trained on internet-scale datasets, but as I mentioned, the datasets have to be paired, which means you have to have an image and a text associated with that image, which means the datasets are a little bit more rare and difficult to gather. But some examples could be Layon 5B or some X-ray images, selfies, artwork. Both diffusion models and transformers can be used on other modalities. It doesn't just have to be text or images. You could use them on code or audio, or even on button presses. So I've included some PDFs, along with this course, of additional technical reading on deep dives into diffusion models and transformers. So overall, generative AI is an extremely powerful tool for creating new content, and has applications in a wide range of fields from art to entertainment to science and technology. By leveraging the power of machine learning and other algorithms, generative AI models can generate high-quality, realistic content that can be used across these applications. Something that I'm particularly excited about is the ability for these models in the future to share an action space with humans. Currently, for example, many of the image synthetics models work on pixels. But one day soon, they may work by pressing buttons or adding brush strokes in your favorite drawing software.